Hello, everyone. So, thank you for being here in this afternoon session. I will go through you in this. So, my talk is different from the one last year, although many of you were not here. Also, because I keep evolving, you know, in the way I see the brain and the way I see these brain models. And so I will guide you a bit through this and these questions that have been popping up in my mind, mainly, what are these are the basis of cognition in a way, cognitive performance, brain function. Are we talking about waves or networks or both, as we'll see, or neither? As the outline of my talk, I will first show some evidence that we can see in resting state fMRI signals, because this is something when I started directly with the modeling part and modeling correlation matrices, functional connectivity, and then I did a long process of analyzing data and trying to understand what are really the features that we want to see. I will then show a bit on the progress on connectome-based models, and then I will introduce these different concepts or comment on the similarities and advantages of looking at networks or waves. And then I will show some results I found with doing some new experiments. So based on all the evidence gathered and the modeling works, I thought about new experiments and how this revealed some interesting phenomena that are useful for the discussion. So first of all, sometimes we rarely see really fMRI signals, right, the brain activity. So what I'm showing here is like from different slices of the brain, so what we scan in two healthy young humans at rest. We see the slices from the bottom to the top of the head. And even if this looks very noisy and very chaotic, you could say, we see some patterns forming, right? We see that from time to time, the activity appears correlated in different brain areas. And when you look at this for a long, long time, several times, what you find, I cannot, okay. But you can trust me that sometimes we see that there are patterns that reveal the default mode network. Sometimes we see what is called the visual network. So this is just to give you an idea of what really we are seeing. Now, if we take a single time point, for example, here at one slice, we see that there are the signal in different seeds here, they co-activate together. So this is at this time point, 152. But if we look at the two signals over time, they're not always synchronized together, right, these two seeds. From time to time, they seem to be. For other times, they are completely in antiphase. So overall, the correlation of these two signals is like 55. But what does it mean? This is static functional connectivity. So we can place a seed here and see which voxels are more correlated with it. But you see that even at a single scan level, when we place a seed in a given place, we can see a map of connections, right? So these are static functional connections. And when we look at this and average across many subjects, so there are different ways to obtain these maps, we can see that there are specific patterns, and so there's this tendency to try to understand, to look at this from the perspective of a network. So if we parcellate the brain, we can choose different types of parcellation schemes, more anatomically based or functionally based or more geometrical. We can see that there are indeed some network patterns. So, for example, here is the default mode network where the medial prefrontal cortex correlates with the posterior cingulate and the angular gyrus. This is very consistently appearing across different data sets. But there are other networks that appear. And these networks have been associated with different psychiatric syndromes or symptoms or even processes, it's just such as cognitive control, the dorsolateral prefrontal cortex. So there's an interesting idea on these networks. But the thing, as you've seen in the videos, is that these functional networks, they appear only from time to time. So when we have these static correlations, it does not capture really just the occurrence of functional networks. So they are short-lived, they are recurrent over time, and this is what drives then the static correlations. But to assess their meaning for cognitive function, it's important to have ways to detect them at the instantaneous level, right? So there have been different over the last decade, let's say, there's this interest in analyzing dynamic functional connectivity. But there were several limitations. In particular, for example, we need to use a sliding window. So we were seeing functional connectivity over a sliding window. And in 2012, Enrico Glerian proposed to use this instantaneous measure of functional connectivity, which is at each instant of time, we take the phase of the fMRI signal using something called the Hilbert transform, and we calculate at each instant of time the phase synchrony as the cosine of the phase difference. So two areas here that have red, it means that they are completely aligned. The cosine of 0, so the phase difference is 0, is 1. And when they are out of phase, it will be -1. But doing this, we can get instantaneous connectivity matrix, let's say, where here you can see it's still noisy. So this is a transformation of the data. These are for all the brain areas. We see how they are synchronized in phase over time. It looks noisy, but again, we see some patterns that appear and disappear. So sometimes we see here a cluster of our other, those squares mean that some brain areas are synchronizing together, but it's clearly non-stationary, and it's still very noisy and hard to compare between subjects or between conditions. So the results using this approach, although insightful, they are still weakly replicable. So the idea to go even further and to understand what was going on is to reduce it even like we have this matrix over time that has a lot of elements, like 90 times 90, so 8,100. So this is symmetric, so it's half of this. But this matrix actually is a rank 2 matrix. So for the ones who understand it, this means that when we can decompose this matrix into two components, let's say, that are described by two eigenvectors. So this is the outer product of the first eigenvector. So this gives a square, like this, the same matrix. And this is weighted, let's say, by a corresponding eigenvalue. And then this is the second eigenvector, again, weighted by its eigenvalue. And when we sum these two, that are represented only each one by one eigenvector and its eigenvalue, we get a matrix that is exactly the same as the original matrix. So the correlation is 1. And this is described only by half of these elements. And what then we found is that this one, since there are only two, this one always represents at least 50% of this matrix. So we can reduce 50% of this signal, at least 50%, using a single eigenvector. So this eigenvector, let's say again we have the matrix, we take the leading eigenvector, and it's a vector. Okay? How do we go back from this to the brain? This is because this matrix here has this vector has the same number of elements as the brain areas that we use in the parcellation. So each element in the eigenvector corresponds to a brain area. And we can use the sign here in the eigenvector, means that all areas with the same sign covary in phase together, and areas with a different sign vary in phase together, but in antiphase with the rest, with the areas in blue. And by taking this reduction, let's say, we can see the evolution of this connectivity matrix by looking at the dynamics of the leading eigenvector over time. So here I'm plotting links between the areas that shift their phase, you see, that are in antiphase with the rest of the brain. And by looking at this, again, now very noisy, we see that there are some patterns that reoccur over time. From time to time, you will see the dorsal attention or the default mode network, but still very noisy. Okay? Now what we do is we take all these eigenvectors over time that are recorded, and we apply a k-means clustering, which tries to cluster these eigenvectors and see, for example, in k-means you tell the number of clusters you want to divide the sample into. And for example, if we divide into 5 clusters, we can see the cluster centroid, which is the average of all the eigenvectors assigned to a given cluster. And we see that the typical or canonical resting state networks or functional networks or intrinsic connectivity networks appear. For example, here is the default mode network, the dorsolateral prefrontal cortex, the somatomotor, or the visual. And there's always a first one. The first one is always everything is with the same sign. So it's more like there's no particular subset of areas that is being separated. So when we apply this k-means clustering to these dynamics, like for several subjects and everything, we can get a repertoire of recurrent functional network patterns. Right here, for example, for k equals 7. And this, if each of these crosses represents one of these centroids, and we look at the dynamics over time, it seems like brain activity can be interpreted as a trajectory in this state space. Imagine each of these crosses is like an attractor of the system, or a pseudo-attractor. We still don't know how stable they are. But this is a perspective that allows us to characterize brain activity in a different way that, as I will show, allows us to compare across subjects. So now we can obtain, by counting how many time points, for example, a given state occurred, or this is a given scan, for example, from a scan from a subject, we can have the fractional occupancy of each of these functional networks. So in total, this would be 100%, the sum of all the probabilities. But we can tell that, for example, the default mode network appeared 20%. And these type of metrics allow us to compare between subjects. We can also look at the probability of transitions over time. So we can see when you are in a given state, what's the probability that in the next time point you will still remain in that state. So this will be state number 1, which is the global state, for example. And the probability to remain there, it's 77%. Then with 8% probability, it can switch to state number 2, which will be the default mode network. This is an average across 100 people. We also look at the variability of these transitions, but this is representative just to show that from time to time, it switches to these other states of activity. These states have less. Here in the diagonal is the probability of remaining in the same state. They have less stability than this one. And whenever you are in any of these states, there's always higher probability to return back to state 1. So you see, you are here, jump here, then with 20% probability, it will decay, because it looks like this one would be the main attractor in the system, and the others is what we propose to call ghost attractors in the system, in the sense that they are recurrently visited, but whenever they are visited, the activity doesn't last there for too long. Actually, with the temporal resolution of typical fMRI, if we don't smooth the data in that, it seems that they occur 1 or 2 time points before they decay again. So using this type of approach, like calculating the relative occupancy or the transition probabilities, we can compare different groups in terms of data, so large data sets, and we can say, okay, are there differences in probability? Here was older adults that were characterized according to their cognitive performance. This was from a larger sample of 4,000 people that were interviewed, but only we took the 40 best performers and the 40 worst performers were scanned, and we found that the good performers had significantly more of the global state, so more stability, less excursions to these ghost attractors, and there were also significant alterations at the level of the transition probabilities. This was in 2017. As you see, the renderings and the models keep evolving, but the concept of the method is the same. This also allows to compare, for example, within a scanning session, we have here was a study where the subjects were infused with psilocybin, which is the active ingredient in magic mushrooms, inside the scanner. So there was no change in the position, and in another session they were infused a placebo infusion, 2 weeks, less than 1 week apart. So here we can see, is there a significant difference between this session here and the others in terms of occupancy of these networks? And here it's visually, but this is a single case. But we can see that the red network, you see here, doesn't appear now in the session after psilocybin. And this was consistent across all the scans. But another thing I want to show, for example, state number 1, here it really illustrates during the time points where it's blue, this is the global signal, all the signals go together in phase. And then here you see that it's red, some signals go up while others go down. So there is this effect that will be important because wave patterns have this property. So when we compare the occupancy of these different networks, now here we clearly see that after the infusion of psilocybin, this was a very, very strong effect. This specific network that is associated with cognitive control completely decreased. And there was an increase in the baseline, the main attractors. So it seems that the psilocybin did not affect the different networks, but had a very specific modulation on a specific network, which is very interesting. And although this was a small data set, these results were recently replicated in a completely new study, also using the LIDA method, but they had a new data set on psilocybin, and they also found a decrease in the lateral frontoparietal network. So there seems to be some replicability and some solidity in these results. Then we applied, for example, this method to schizophrenia data, because it's also interesting for psychiatry. And what we found was that in patients with schizophrenia, there was significantly reduced stability of the global mode, right? And there were more excursions to these ghost patterns. So even during rest, when they are not being perturbed with any task or anything, we can see that in the resting state, the patients with schizophrenia exhibited more of these transitions, and also they were associated with task-related networks like visual, somatomotor, limbic. But in this data set, there was not, we didn't associate with specific symptoms, but it would be nice to see if there is a relationship even with the symptoms of schizophrenia. So very briefly here, I showed already difference in terms of cognitive performance in healthy people, modulation by a drug, change in schizophrenia, in psychiatric disorder. But there are things such as music listening. What we found, that only a specific pattern significantly increased. This was, the p-value was 10 to minus 7. There was a shift here, as you see, in the phase of only the signals here with respect to the rest of the brain was what really distinguished between groups. And this same or very similar pattern was also found to be activated by deep brain stimulation, or even seeing happy babies. People had to score the happiness score of the children inside the scanner. And so to summarize overall, this occupancy you saw in the video, sometimes we can see the function, the default mode network appearing, appears to be a fingerprint of the people. And in healthy people, there's a healthy range of how much these different modes or functional networks should appear. The results are moderately reliable, so the same person scanned twice can exhibit similar probabilities. For example, it's visual by eye. I've analyzed data sets where some people show a lot of global fluctuations in one scan, and then 2 weeks later we see again more of global fluctuations. These values seem to be altered in different types of psychopathologies or neuropsychopathologies. We've analyzed data sets on major depressive disorders, schizophrenia, autism, even more recently people experiencing auditory hallucinations. We're also seeing some interesting results in obsessive compulsive disorder, and even in symptoms that are not even clinical in the sense like the capacity of self-reflectiveness, or when people are suffering, they are not depressed, but they are sad because of a relationship breakup. So we could find alterations in networks that involve the DMN and the precuneus. And then another thing that then is also important, so not just to use this as a biomarker potential, but also as how to give us insights of how we can tune these values. So if we find some disorders have these networks are altered, how can we modulate this? So it seems that psychoactive compounds have an effect, but also brain stimulation, as I will show, and we have used this in computational models to define the brain state trajectories and even natural stimuli. Okay, so we have this evidence. And now, how are we going to explain what is going on? So when we look at this dynamic functional connectivity, right, it's dynamic, but it's the first guess, an obvious guess, is to look at the underlying structural connectivity, right? Are these functional connections related with the underlying structure? So when we look, but this is static, of course, and it's important to make the link, we need a dynamical model. Right? And this is where comes the link with the previous slides. But I will be very illustrative, let's say, and try to convey these terms, avoiding using very detailed equations, but also trying to explain what they mean. So network dynamics can be explained or is described by a system of coupled differential equations, like we heard before. So a differential equation describes how something, any type of signal, evolves in time, any types of variable. And this, when they are coupled together, so in a network, these functions are coupled together, there's one part of the function describes how the node behaves over time, even in the absence of input, right? And then there's a term that describes how the input from the other nodes is integrated there. And as you can see, very rich dynamics can appear, and depending on different models that we consider, we can, and the idea is to see, okay, if we put the connectome there, do we see these functional networks appearing? So interestingly, so here I will go a bit through the history of these connectome-based models. So in 2009 came this paper. This was right when I started my PhD, where Christopher Honey used for the first time the human connectome structure. So they used the structural connectivity. They applied a dynamical model, and they showed that they could reproduce patterns of functional connectivity. So this is the structural connectivity for the right precuneus, for example. We see with respect to all other brain areas with which they are connected. And this was the empirical functional connectivity. So what was being puzzling people is that you see positive functional connections, sometimes even between areas that are not structurally connected. So by applying this nonlinear model to the structural connectome, they were able to replicate with very good agreement in some cases, in particular for some seeds, the empirical functional connectivity with the model. And this here they show for different seeds. So this was really impressive. And so far, like the field, this is almost one of the most successful, like in terms of fit of models. But there was no dynamics in it, right? The fit was to fit the static functional connectivity. So then, let's say, then in a work led, there have been many works, and maybe I'm not citing all of them, but here are the seminal works that will make my point. So then a work led by Victor Girsa, together with Gustavo, by Enrique Hansen, where they aimed here to model the switching behavior between states of functional connectivity. So this is a time versus time matrix, and shows how the activity, for example, here there was a given state, the state alpha. So how after some time, the same state alpha can reappear. So they managed to show that with these models, there is a repertoire of attractors in this system of coupled dynamical equations. There are multiple solutions to that system. Those are the attractors of the system. And the idea was to show that when you simulate with a dynamical model, the simulated activity switches between the attractors of the system, and some of which were shown to spatially overlap with functional networks from the literature. I put here some of which because it was not exactly like the first network, so the simulated dynamics generated many patterns, and they were selected. Like here, what are shown are the ones that that showed a spatial overlap with these networks. But already it's an advance to go beyond the static functional connectivity, and this is a very relevant paper. Then the other was not fitting the relative occupancy, let's say, of the states. And then in a work also with Gustavo, Deco, and Martin Kringelbach, we discussed that it was important that not only to model the functional connectivity, also the switching behavior, but also the relative occupancy, like we were seeing with the LIDA states, right? So the idea was that if we characterize two different states here, X and Y, by their relative probability of the different substates, let's say, the idea is to find how can we stimulate the model. So first, how to make the model fit this probability or occupancy of the state that was called probabilistic metastable substates, so the PMS, let's say. And first to fit the model to predict this PMS, and then what would be the stimulation strategies to make the system switch its PMS distribution, let's say. But here again, so it's a conceptual advance in the sense that we are trying to model or to characterize brain states based on the relative occupancy of the different networks. But here there was no aim to match the spatially the functional networks. So the idea, we just cluster the activity into the first three states with k equal 3, for example, and then the idea was just to see how to change the relative stability of the different networks. So there's still some advances that need to be done at that level. But here, just as a summary, these connectome-based models have served to test and validate hypotheses for the generative mechanisms of functional networks, their switching behavior, and their relative occupancy. And they are now evolving to inform perturbative strategies, right? But to serve for neuropsychiatry, we still need to find out how to precisely and effectively modulate the stability of the specific functional networks that are altered in disease. So we need more specificity. We need improvements, and we've been, so only in this last year we had 3 works, one of them with Daniel Curtin, who is here, like trying to see how we can move from this phenomenological to predictive modeling, right? How can we really model brain stimulation in silico? How far are we? Of course, we've seen this morning with Victor that it's working for epilepsy, but it's still not addressing the functional, the fMRI and the functional networks. And this is also something that needs to be improved in that direction. So here I will bring now, this is the third part of my talk. Let's see how far I am, it's okay. So we had this dynamic functional connectivity. We try to see how this can emerge from interactions in the static anatomic connectivity. But this network approach complete or just a perspective? And I put here a typical image where we may be seeing this, we try to explain it with this, but then maybe we're also missing another part, right? So sometimes we're never seeing everything. And specifically when we look at the brain and these network patterns, we assume that when we see like 2 areas that are correlated together or part of a functional network, that they are the result of the propagation of some sort of activity across the structural network. But this is not explaining some things, like here I put a blue seed. It means that whenever the signal here goes up, it will go down here and vice versa. So there are these simultaneous co-activations and co-deactivations that are not very well explained using coupled the bold signal alone. So there is now more and more, like say, theoretical proposal. So this is not yet like an established theory, but there's an idea that what we may be seeing may be associated with the phenomenology of resonance in a continuous medium that is not totally exclusive with the other, like as Victor said, if this was a very highly detailed continuous medium that with millions of units together, it can approximate what we see here and could indeed resonate as well. But indeed this, if we just look at it like this, these are fundamentally distinct mechanistic scenarios for the same observation. So this hypothesis is just to go over it, but this is long before 2012, the idea that the modes that we see not only in fMRI but also in EEG, MEG are associated with modes of resonance that could be explained by the harmonics, the spherical harmonics, but adapted to the geometry of the brain. There have been attempts to use even the connectome, as I said, the high-resolution connectome as a graph, and then apply the graph Laplacian to infer what would be the modes of this network, so these harmonic waves. But this is at the network level, and more recently, as James will show in the next talk, it has been shown that we can also estimate these modes of resonance not from a high-resolution or dense connectome, but from the surface mesh of the brain. So in a way, the geometry alone, without even considering the anatomical neuronal connections, can explain these things. But there is what I think, and what I will now show you, is that I think more evidence supporting this hypothesis is needed, or more tests to validate and to see what is going on. But what I think is captivating from the waves perspective is that this it's a universal principle in bounded systems that you can see as a 1D, 2D, 3D. This would be in a room, imagine the particles. So people usually think that standing waves are the result of two traveling waves that interfere together. But you can have standing waves even without things moving from one place to the other. But the key properties here that I want to make is that these are properties of the system, so each system can have multiple eigenmodes, as many as the number of degrees of freedom. They are defined in space, they oscillate in time, and they are determined by systemic properties, so by the whole, by the geometry, by the entire network, by the shape of the room, by the boundary, the surface tension, the medium, elasticity of the medium. And if we knew all these parameters, we could indeed predict analytically the modes. But the modes can be there, so they can be part of the repertoire, but they could never be activated, right? And so these modes can be triggered by perturbation at the natural frequency or by a single pulse in an antinode or a given place, like you know from any musical instrument, when you play one note in the piano, it will trigger a given note to be played, or even when it's perturbed with noise. This is another point I want to make here, that noise contains all the frequencies. So if we're perturbing with white noise, from time to time you'll see the resonance of all the modes of the system, right? And another thing is that when triggered, distant poles covary together in phase or in antiphase, you see here, and there's not necessarily a direct connection between the different nodes. They are just different poles, and by changing the mode, you will see different patterns of connectivity. Also here, I put them all oscillating over time forever. There's no change in the amplitude, but as you know, in all musical instruments, when you play a note, the amplitude eventually decays over time. So these modes are in a subcritical regime. Whenever you receive an input, it will do an oscillation until it decays over time. Okay, so this could explain how different points in a system can be correlated together here and anti-correlated with an area in the middle. So this is just to make my point, that if you just add noise to a system, you can see different short-lived long-range correlations and anti-correlations in any system with coactivations and activations, and different modes could resonate at the same time. Now, when we take the modes that I was seeing with LiDAR, remember the default mode, so this is what I obtained for k = 8. This is now a data set of 1,000 different people, let's say, and I have the global mode. When I look back at it in voxel space, so I take the fMRI volumes, I compute the eigenvectors, in voxel space and average together all the ones that were assigned to mode number 1. So we see here all the signals have the same color, so it means they are covariant in phase. When the default mode network that we typically put just the seeds and we look at it from a network perspective, we clearly see that there is this anti-phase locking. So we could kind of say that there are nodes and anti-nodes. So the points of no motion would be the nodes. The anti-nodes are either the deep red and the blue. So, but each of these waves, so this would be the default mode network in voxel space, the visual network in voxel space, the ventral attention, the limbic. So we clearly see that this is a very macroscopic phenomena, right? So they reveal wave-like patterns, okay, spatially. Most of these patterns do. Here again, just to see here how the eigenvector looks like when it's sorted. Here it's really the left and right posterior cingulate, the left and right angular gyrus, and the medial orbitofrontal cortex. And this significantly differentiated between controls and people with autism. So it's important to understand what these modes are made of so that we can think of strategies how to perturb them and how to activate these modes. So here, just going briefly, that there are different ways how to, sorry, there's a D missing, how to determine if components of a system are modes of resonance. So, there's this way to use the Laplace operators. Let's say there are different ways to solve the Laplace eigenfunctions using the surface mesh or the graph or whatever, but it's to estimate the modes of diffusion through space using this Laplace operator. But if we just kind of record, like when we see with fMRI, so we have an empirical observation and we want to capture the modes or the eigenmodes from the system, we could simply just do the covariance eigenvectors. And it's when these two meet, right? See how well your predictions fit the observations that we know that we are having a good prediction. But in terms of moving here, so another characteristic of these eigenmodes is if they oscillate in time. So whenever you would see the spontaneous stochastic resonance of a mode, if it goes up and down, if there's like a reverberation of the activation, that would be a signature of resonance. And so, but the key here, and here is the last part of my talk, the key was to see, when you look at the fMRI signals, we cannot clearly see this oscillatory nature or this reverberation in the wave patterns because the temporal resolution is very slow. So the idea is to see how fast can we go with fMRI. What if we choose a slice? We know there's a slice. There was this paper in Nature Neuroscience even last year showing consistency, agreement. This is the default mode network. So whenever there's this activation here and here, it appears in all the rats across different labs. And one of the groups collaborating with this, for this consortium was Noam Chamesh, who is in Portugal, that has a high-resolution scanner with a cryogenic probe. And we went there and we saw how fast can we go if we just focus on a single slice. Okay, so we know here we can see the MN. I want to see if this oscillates. And so we took a slice of the rats, and then we did a type of a paradigm. So we gave a sedation, and then we added more and more isoflurane. But I will not go into that in detail. But I want to show you that you saw, like, this is a scan of the whole slice, okay? And I didn't manually do a mask. I only showed the voxels that had power in these slow frequency ranges. So we see in this specific, that there's really some signal here propagate across the cortical sheet, right? Here I show this is equivalent to one convolution of the human brain, you know, just to have a notion of the scale. But even at this small scale, we see from time to time here, you see the so-called pattern associated with the default mode network, and this seems to be oscillating. So we further analyzed this is to show how much the same pattern is appearing across different rats. This is without any thresholding and without any and broader bands. And this is to show also, we also did scans on multiple slices to show this doesn't appear only in these slices, but appears across different slices over the entire brain. But here the TR was smaller, but still we see that this is a whole brain process. So when we had these covariants, these principal components that are the eigenmodes of covariance, what we found is that they are indeed oscillating between positive and negative representations. So I think and we can get a time series associated with each pattern, and we see, so this is the coefficients over time, okay? And the coefficients over time oscillate. So we do the power spectrum, and they oscillate between positive and negative. So if I just plot here mode number 2, which is the one associated with the default mode network, multiplied by its temporal signature, we see that, you see, it's switching between positive, negative, right? I finished my 40 minutes. But so this drives, let's say, long-range functional connectivity and also anti-correlations, right, which cannot be explained. So we analyzed the peak across, we had 12 scans, and then we see for each of the scan, what is the peak frequency of each of the modes, and what is the resonance Q factor, which is a measure that evaluates like how narrow is the peak and how fast, so it's kind of proportional to the number of sustained cycles. So the one I was showing you before in the video was for one of these rats that had like around 10 sustained cycles every time the mode was activated. So we can do the autocorrelation function, and here comes the link with the previous studies. So when we have the autocorrelation function of each mode, remember, we can see how many times it reverberates before it decays to a given threshold. And if we do the Hilbert transfer of this to see, this means that whenever that pattern is activated, it will decay back to the static point with a number of cycles. This is the same as you see a wave or a drum, let's say, and it will do like until it returns back to the baseline. So what does this look like? We heard this morning, it looks like a damped oscillator, right? So it means that it can be modeled, like we discussed with Vitor in the panel now. Can we use just a phenomenological description without really understanding what this is? Using the Stewart-Landau equation, we can model these different activity patterns. And using the Poincaré, I added also this slide diagram, we made this effort in trying to characterize the behavior of different dynamical systems. And we see that one of the descriptions is this spiral sink attractor, right? And there are these saddle points, single points. So these things are inspiring because even if we are not seeing them in different perspectives, so we see this type of spiral sink return to the fixed point, we can use the same type of equations that describe this. So the idea was to use this is the Stewart-Landau with 3 different types of parameters. With one, there is no damping coefficient, so the A is positive, so the system will oscillate over time, that's the gray. So whenever it is, so the arrow means a stimulus, and the system would just stay there oscillating forever. If it's over-damped, whenever it's activated, it will decay back to 0 immediately. But when it's in this under-damped regime, it means it will decay back to the fixed point with an oscillation. And if you perturb this with white noise has all the frequencies, this equation will have just a very narrow peak frequency. So it conserves the angular momentum. You feed in noise, but then all you get is just everything in the same natural frequency. And this was to show if it's overdamped because it's more associated with. Okay, so there was a problem here with the equations, but with the symbols. But basically, the idea is now we have all these modes that we will not know what they are, but let's assume that they are wave patterns or standing wave patterns, and we will make them vibrate or oscillate using this Stewart-Landau equation added with white noise. And we fit the A based on the damping coefficient recorded empirically, and we fit also the natural frequency. And the idea was then to model this as some Imagine if you had these different modes just summed together, activated with noise, does it replicate what we usually observe, like different snapshots of functional connectivity, let's say? So the idea is that what we see, this is what we record, right? We see these waves. This is the broadband really signal without any filtering or anything captured with fMRI. So we see these patterns that appear noisy, but that there's some structure there. From time to time, it seems we see the default mode network, but it's not very clear. It can be decomposed in very fine-tuned notes, let's say, that when you sum them together, you retrieve this activity or what is hidden there in this activity. And this approach of the wave superposition principle, let's say, so based to this superposition, is that the resonance of an eigenmode would drive these long-range correlations and anti-correlations, and then when you have multiple standing waves, you can generate traveling wave patterns. So not only traveling waves can generate a standing wave, but multiple standing waves can generate a traveling wave, like Victor also said this morning. Okay, so overall, okay, so this is just to finish that I'm not sure yet what, okay, so everything is parts, different pieces of the puzzle that we're still trying to put together. So the dynamic functional networks, this wave dynamics, network dynamics, I think everything plays a role. There are some interesting things coming out with fluid dynamics and also in ionic waves propagating through the cortical sheet that may bring additional insights in the future. But overall, as a message for the audience and people here, is that we need to understand the rules, which is crucial to develop better models for intervention. We cannot do just trial and error. We need models, right? And despite these theoretical advances we've shown today, even in this session, even my work, it's important that everybody understands this is scientific theories that are imperfect by definition. So there's always room for improvement. And the efficiency of these brain perturbation strategies is still suboptimal, not to say embarrassing. And so, and this is really a problem, because if you take together all the psychiatric disorders, neurodegenerative and disorders of consciousness, there's like 20% of humanity, and we have high chances to be suffering from some of these in the future. So the clock is ticking, and there's a lot of work to do, and we are counting on you. And that's it. Okay, so there are 3 posters I'm collaborating with during this session. I invite you to come, and thank you, everyone.
Thanks very much, Joana. Real tour de force there. We're running a little bit over time, so I think we have time for one question while James is getting set up. If anyone can be quick to the mic there. Yeah, okay. And try to keep it brief.
Okay, just a quick question. How do you think, if at all, it relates to EEG microstates?
That's a very, very good question. I think indeed understanding the link between what we see in EEG and fMRI is like a holy grail that I don't know if I will see it happening in my lifetime. So the mechanistic hypothesis of resonance and spherical armor, and that has been proposed in particular for EEG microstates, are the patterns you see. And in particular in EEG, you have always these red-blue patterns that some people naively say, okay, this is long-range inhibition that is driving the negative response. So there are some puzzling observations that are still not fully explained, so there's still a lot to solve and to understand, but this is not at the same scale of what we detect in EEG, and I didn't see any EEG frequency in this scan, so there may be, I don't know, it's really an open question, but good question. And now I pass the microphone to James.
Okay. Thank you again, Joana.